Good morning to all. This is Uma Shankar, working as a lecturer in EC at Government Polytechnic College, Kozhikode. So today I am dealing with the subject Advanced Engineering Mathematics for Electrical Engineering students in 4th semester. So today my topic is on Laplace transform. In this I am going to discuss about the application of Laplace transforms to the differential equations with constant coefficients. In the previous class we have seen how you are going to apply the Laplace transform for the different methods. That is nothing but the Laplace transform technique is applied for the first shifting theorem. So that is how we are going to apply the Laplace transform for first shifting theorem and derivative functions, and also the multiplication by T method and division by T method. And next we have seen how we are going to apply for the evaluation of integrals for a given Laplace for a given function. And next is we have seen the inverse Laplace transform by using the multiplication and division by powers of S method, and also using the partial fractions, how you are applied this inverse Laplace transform for a given partial fractions, and also by convolution theorem. So now in this class we are going to discuss about how you are going to solve or how you are going to apply this Laplace transform method for a given differential equation. Okay, so here the differential equations are of two types. One is homogeneous differential equation, and next one is the non-homogeneous differential equation. Now we will see a problems on this homogeneous and non-homogeneous, how we are going to apply this Laplace transform, okay, for a given differential equation. So now previously when you are going to evaluate the ordinary linear differential equation or non-homogeneous ordinary differential equation with constant coefficients, so first what we have to do, so we are going to find out the general solution, and then after that we are going to evaluate the arbitrary constant. Okay, so instead of that we are going to use a simple mathematical process or mathematical technique. By using the Laplace transform we can make a analysis very simple way. That is nothing but we are going to solve the any differential equation in a simple way or in an easy way. The previous methods are very complex method, and it is a very lengthy method in order to get the required solution or the general solution. But in the case of the Laplace transform, it is a very simple method in order to get the general solution. That is nothing but whatever the solution you can obtain from the homogeneous or non-homogeneous differential equations with the constant coefficients, so which will be simple by using the Laplace transform technique. Now we will see the steps how we are going to solve when a differential equation is given by using the Laplace transform method. Okay, so the first step is nothing but, so whatever the differential equation is given, so first what we have to do is nothing but you have to take the Laplace transform on both sides for a given differential equation. So next step is, so you have to use these formulas when you will apply the Laplace transform for the differential equation. That is first order equation, second order, and third order. Okay, it is if you have the Laplace transform y double dash of t, okay, that it can be represented as s into y of s minus y of 0. Next, if you have the Laplace transform y double dash of t, then it can be represented as s square into y of s minus y of 0 and minus y dash of 0. Similarly for the third order differential form, that is equation. Okay, so this y of 0, y dash of 0, y double dash of 0 are nothing but your initial conditions. These are nothing but initial conditions. So these initial conditions may be given in the problem in order to get the required solution. Okay, if it is not given, then you have to assume that these initial conditions are equal to 0. Okay, right. So replace y of 0, y dash of 0, and y double dash of 0 using the given initial conditions, which is nothing but step 3. So next in step 4 and step 5. So now we have to simplify the given equation in such a way that the final equation can be represented as y of s is equal to that the numerator function by the denominator function. After substituting all the initial conditions, then finally we will get the equation as y of s is equal to the numerator function and the denominator function. Now the entire function is represented in terms of s. Before applying the Laplace transform, it is in t. Now after applying the Laplace transform, that it is converted in terms of the S domain. Okay, it can be converted in terms of the frequency domain or S domain. Okay, now what we have to do, so after getting the function, that is after getting the y of s function, now to resolve this function by using the that is partial fraction method. Okay, you have to simplify the given function by using the partial fraction method. So after resolving the function by using the partial fraction method, now we have to apply the inverse Laplace transform in order to get the y of t function, which is your required solution for a given differential equation, which satisfying the given initial conditions. Okay, so these are the steps you have to be follow whenever a differential equation is given with an initial condition. Okay, these are the 7 steps you have to be followed. Now we will see a first homogeneous differential equation. Okay, so when how you are going to identify whether it is a homogeneous or non-homogeneous? Whenever you are giving the homogeneous differential equation, it is of the type. So at the LHS side, you will have the differential equation form is equal to 0. So if you have equal to 0, then this type of differential equation is called as a homogeneous differential equation. Along with this equation, it contains the initial condition. So y of 0, he has given the initial condition y of 0 is equal to 1. Next is y dash of 0 and y double dash of 0 value is equal to 2. So wherever you will have this initial condition value, you have to substitute the value as 1 and 2 in the given initial conditions. Okay. Now this differential equation can be simplified. Okay. Now this differential equation can be simplified or it can be represented in a short notation. So we have the different forms of differential equation, all are same. So if it is represented in this way, d cube y by dt cube, and this can be sometimes represented as d cube, or it can be sometimes represented as y triple dash. Either you can represent in this form or in this form or in this form. So finally, whatever it may be the form. So if the differential equation is represented in this form, it has to be finally converted in this short notation. Okay, right. So d cube y by dt cube can be represented as y triple dash plus 2 into d square y by dt square can be represented as plus 2 into y double dash, next to minus y dash, next is minus 2 into y is equal to 0. This is your the simplified form of the given differential equation, that is short notation form. Okay, so then what we have to do next? So step 1 is nothing but applying Laplace transform to the given differential equation on both sides. Okay, so after applying the Laplace transform using the linearity property, so we have to whatever the Laplace transform will apply to this differential equation. So this is a combined Laplace transform. This is the sum of combined equation of the, we have to apply the Laplace transform to the combined differential equation that can be divided as, okay, the sum of Laplace transform of the separate functions of the individual functions. Okay, right. So that is about your linearity property. So now we have to apply the Laplace transform to the individual function. Laplace transform of y triple dash plus 2 into Laplace transform y dash minus Laplace transform of y dash. Next is minus 2 into Laplace transform y is equal to Laplace transform 0 is nothing but 0. Okay. So now we have seen that what is the formula for Laplace transform y triple dash? That is s cube into y of s minus s square into y of 0 minus s into y dash of 0. Next to minus y double dash of 0. So this is for Laplace transform of y triple dash. And similarly, you have to apply the Laplace transform of y dash. Okay, we know the formula for Laplace transform y dash and y double dash, y double dash and y dash and Laplace transform y. So in place of Laplace transform y double dash, s square into y of s minus s into y of 0 minus y dash of 0. Okay, and similarly for y dash, s into y of s minus y of 0. What is Laplace transform of y? That is nothing but your y of s. Okay, right. So now second step is nothing but, so we have applied this formula for a given Laplace transform for a given differential equation. Okay, derivative functions. Okay, all right. Now what we have to do third step? So we have to apply all these initial conditions wherever you will have in this equation. So here you will have y of 0, y dash of 0, y double dash of 0, y of 0, y dash of 0. In all these places, you have to substitute these initial conditions and you have to simplify this equation. Okay, you have to simplify this equation. After substituting the initial condition, the equation is represented as in this way. This is your final simplified equation after substituting the initial condition. Now this equation has to be simplified in such a way that it has to represent the y of s. It has to finally represented in terms of the y of s function. So now this can be simplified as s cube into y of s. Next minus s square minus 2s minus 2. Now this plus 2 will be multiplied to this internal term. You will get as a plus 2 into s square y of s plus into minus minus 2 into s 2s plus into minus minus 2 into 2, that is nothing but 4. Next is this term minus s into y of s minus into minus, this will be the plus 1 minus 2 into y of s is equal to 0. So now we have to take all the y of s terms at the LHS side, okay, and remaining terms to the RHS side. So if you take this y of s term as common, and if you take all these y of s terms to the LHS side, then what you will get finally? So if you take the y of s term as common, that you will get the first term as s cube. Next is plus 2s square. This is the second term, and the third term will be minus s minus s. Next is minus 2. That is minus 2 into y of s. So I have taken this y of s common in all these terms, and finally we will get s cube plus 2s square minus s minus 2. And remaining minus s square, here you will have only one minus s square term. If you take this minus s square to RHS side, then you will get it as a plus s square, okay, which is represented here. And next we will have the s terms. You have to check for s terms. Minus 2s, here we will have the minus 2s, minus 2s, minus 2s, minus 4s. Okay, and we don't have the s terms here, only two s terms are there. Minus 2s, minus 2s, minus 4s. If you take this minus 4s to RHS, you will get it as a plus 4s, which is represented here. And next is the constants. Minus 2, minus 4, minus 6, minus 6 plus 1, minus 5. This minus 5 will be shifted to RHS, then we will get it as a plus 1. Okay, and so finally we have to get this y of s function. Okay, this is your step 5. Okay, y of s is equal to, so here you will have the s cube plus 2s square minus s minus 2. It is in multiplication at the LHS side. So now this term will be shifted to RHS side, that you will get into the denominator. Okay, so y of s is equal to s square plus 4s plus 5 by s cube plus 2s square minus s minus 2. Okay, this is the final function which is represented in terms of y of s. Now this has to be simplified. Now this function has to be simplified. So in this case, if you see in the denominator, this function, now we have to evaluate the roots for the given equation. Okay, you have to find out the roots of the given equation. Okay, how we are going to evaluate the roots of the given equation? So this is the third order equation, s cube plus 2s square minus s minus 2. This is the third order equation. So by using the trial error method, so by putting the value as 1, so s is equal to 1 or minus 1, 2 or minus 2, whatever it may be. So by trial and error method, so whatever the value you will substitute in this s, it is either 1, minus 1, whatever it may be. So the entire equation has to be is equal to 0. Okay, the entire equation has to be equal to 0. So if you substitute s is equal to 1, this entire function or equation will be equal to 0. Now s is equal to s minus 1 is equal to 0 is one of the root of the given equation. That is s is equal to 1 or s minus 1 is equal to 0. This s is equal to 1 is a root of this given equation. So next, by using the division method or Horner's method, then you have to evaluate the other roots. S is equal to 1. Okay, now we have to take the s cube quotient. What is s cube quotient? 1. What is s square coefficient? Plus 2. What is s coefficient? Minus 1. Next is constant, minus 2. So first value you have to substitute as a 0 initially. So 1 plus 0, you have to add these two values. Okay, 1 plus 0 is nothing but 1. Whatever the value you will get here, that has to be multiplied with this root value. That is this 1. 1 into 1 will get it as a 1 here. You have to substitute here. 2 plus 1, you have to add these two values. 2 plus 1 is nothing but 3. Now then you have to multiply these two. 3 into 1 is nothing but 3. You have to put that value here. Minus 1 plus 3 is nothing but 2. Add these two values, you will get 2. So this 2 is multiplied with respect to this one. That is 2. So minus 2 plus 2 is nothing but 0. Definitely we will get a 0 when this is the perfect root of this given equation. So now this will be, this 1 is the coefficient of s square, this 3 is the coefficient of s, and this 2 is the constant value. Okay. So finally we get 1 into s square plus all these values are plus values. That's why plus 1 into s square plus 3 into s plus 2 is equal to 0. This is the equation. This is the another equation. Now we have to evaluate this equation. That is nothing but s square plus 3s plus 2 is equal to 0. So by using this, you have to find out the another two roots of the given equation. That is plus 2s plus s is equal to plus 2 is equal to 0. From this s into s plus 2, next is plus 1 into s plus 2 is equal to 0. So finally it becomes s plus 2 into s plus 1. Get s plus 2 into s plus 1. Total how many roots are there? One is s minus 1 is one root. Next is s plus 1 is another root. Okay, and next is s plus 2 is another root. There are three roots are there for the given equation of the function. So these are the roots which is defined for a given equation. Okay, so that has been, so s minus 1 into s plus 1 is represented as s square minus 1, a plus b into a minus b. So s square into s square minus 1 into s plus 2. So that is represented here. This is the way you have to simplify the given function. Okay, that has to be evaluated in order to find out the roots of the given equation of the function. Okay, right. So now this can be divided as, so the numerator will be divided. Again, the numerator will be represented as s plus 2 whole square. Okay, if you expand this, what you will get? S square plus 2ab, that is nothing but 4s plus 4. So here the numerator function will be s square plus 4s. It is satisfied. But here we will have the plus 5. But here we got as plus 4. So then you have to add plus 1 here. So now this entire equation has represented as s plus 2 whole square plus 1. Now the numerator has been simplified as s plus 2 whole square plus 1. Okay. So this depends upon, so the numerator has to be simplified based on the denominator function in this case. Okay. So now the numerator will contain the two terms and denominator, this whole as represented as a one single term. The denominator function is represented as a single term. Now you have to divide this into the two terms, s plus 2 whole square by s plus 2 into, okay, s square minus 1 as one term. Next plus 1 by s plus 2 into, okay, this s square minus 1 can be represented as, after this s square minus 1 can be represented as s plus 1 into s minus 1, s plus 1 into s minus 1. Okay, so in this s plus 2 in the numerator and s plus 2 in the denominator will get cancelled. Finally we will get s plus 2 by s square minus 1. Okay, okay, s plus 2 by s square minus 1. Okay, all right. So this is the simplified equation what I have derived previously. Okay. So now this again the numerator will contain the two terms and denominator this whole will be considered as a one single term. Now this one divided into the two terms, s by s square minus 1 as one term plus 2 by s square minus 1 as another term. And now this term can be represented as 1 by s plus 2 and this is divided as s plus 1 into s minus 1. Okay, right. So now this function, this equation is simplified as by using the basic formula, and this equation is simplified by using the basic formula, but this entire function or equation is simplified by using the partial fraction method only. Already we did this partial fraction method in previous class. Okay, now we will see how we are going to evaluate the partial fraction by using this equation or by using this function. So here all these roots are non-repeated roots. Okay, so for non-repeated roots, the partial fraction is represented as a by s plus 2. Okay, and next plus b by, okay, that is nothing but this is plus b by not minus plus b by s plus 1 plus c by s minus 1. Okay, right. So because of non-repeated roots, the corresponding partial fraction, this partial fraction is represented as a by s plus 2 plus b by s minus 1 or s plus 1 plus c by s minus 1. Okay, so now we have to evaluate a, b, c. Okay, now we have to evaluate this a, b, c method, a, b, c values by using the partial fractions. Okay, by using the partial fractions. So now we'll simplify for only a value. How you will get this a value? Okay, next B and C value can be evaluated in the same way how you are solved for A value. Okay, right. So 1 is equal to, at the LHS side, the numerator value. So you have to equate the numerator value only. So 1 is equal to, so this A will be multiplied with the, so these two terms. Okay, remove this term. So you could not multiply this denominator term. Okay, except this denominator term, you have to multiply these two denominator terms to the A. So that is S plus 1 into S minus 1. Okay, or you can take the LCM and you can simplify that. Okay, next is plus B. This is plus B into, again this denominator term will be not multiplied, and you have to leave it this denominator term, and you have to multiply the remaining two denominator term, that is S plus 2 into, okay, S S plus 1, sorry, S minus 1, it is S minus 1. And next is plus C into, again similarly S plus 2 into S plus 1, S plus 2 into S plus 1. So now in order to get the A value, so if you want to get the A value, that is nothing but if you want to find out this A value, so now we have to get the B value as 0 and C value as 0. That is nothing but, so we have to put the S value. So we have to put the S value in such a way that the B term should be is equal to 0 and C term should be is equal to 0. The entire term should be is equal to 0. So if you put S is equal to, okay, if you put the S is equal to minus 2. So in both the terms, you will have a common as S plus 2 and S plus 2. So if you put S is equal to minus 2, then B will be equal to 0 and C will be is equal to 0. Okay, both will become 0. So when you put S is equal to minus 2, then 1 is equal to, so A into minus 2 plus 1. Okay, next minus 2 minus 1. So in place of S, we have to substitute this minus 2 value such that B will be eliminated and C will be eliminated, and we can find out only the A value. So from this 1 is equal to A into minus 1 minus 3. So minus into minus is get it as a plus. 1 into 3 is nothing but 3. 3 into A is nothing but 3A. Finally 1 is equal to 3A, and from this you got A is equal to 1 by 3. You got A is equal to 1 by 3. That is, we got A is equal to 1 by 2. And similarly, we can simplify the B value and the C value in the same process by putting the some S is equal to some value in order to get the B value and the C value. So in this, for the first case, you have to put S is equal to minus 2. For the second case, you have to put S is equal to 1. And for third case, you have to put S is equal to minus 1 in order to get A, B, C values, okay, from the given partial fraction. Okay, so after getting A, B, C values, okay, you have to substitute A value here and B value here and C value here, and that the entire function or equation is represented here in order to get this y of s function. Okay, so now we got this. Okay, this term will be same as the first term, and this one will be same as the second term, and the third term will be evaluated by using the partial fraction. That is, A value will be 1 by 3, 1 by 3 into s plus 2. Next is plus, this is your plus value here. Okay, plus B value will be, sorry, B value will be minus 1 by, sorry, B value will be 1 by 2. That is plus 1 by 2 into s plus 1. Next to C value will be 1 by 6 plus 1 by 6 into s minus 1. Okay, right. So finally, this is the way you have to simplify the given y of s function by using the partial fraction. Okay, so this is the fifth step. Next, what we have to do? So next we have to apply the inverse Laplace transform for the given function, whatever the function which is represented in terms of s. Okay, when you apply the partial fraction, again you have to apply the linearity property by applying the Laplace inverse transform. Okay, so Laplace inverse of y of s is equal to Laplace inverse of this function plus 2 is a constant which can be kept outside, plus 2 into Laplace inverse of 1 by s square minus 1. Next 1 by 3 is a constant which can be kept outside, plus 1 by 3 into Laplace inverse of 1 by s plus 2. And next is minus 1 by 2 into Laplace inverse of 1 by s plus 1. Okay, here we got the B value as minus 1 by 2. Okay, that's why I kept as this as minus 1 by 2 here. Okay, so minus 1 by 2 Laplace inverse of this term plus 1 by 6 into Laplace inverse of 1 by s minus 1. Okay, all right. So now from this Laplace inverse of, we have a direct formula for this. What is the Laplace inverse of s by s square minus a square? That is nothing but, if you see this formula is Laplace inverse of s by s square minus a square. That is nothing but cos h. And this will have a formula cos h. If you have a minus in the denominator, it is cos h, hyperbolic function. If it is plus, it is cos 80. Okay. So in place of a, we'll have the 1, that is nothing but 1 square. So then you will get the value as this as cos ht. Got that value as cos ht. So now if you simplify for the second function, then it is 1 by Laplace inverse of 1 by s square minus a square. So for this, we will have the formula for this 1 by a sine hat. 1 by a sine hat. So what is the a value here? 1 square. That is nothing but 1. So 1 by 1 sine h 1 into 2. That is nothing but 2 into sine ht. Okay. All right. So if you go for the third value, third term plus 1 by 3, and this can be simplified as Laplace inverse of 1 by s plus a. Okay. Laplace inverse of 1 by s plus a. It is of the formula for this is nothing but e power minus at. So what is a value here? 2. So e power minus 2t. 1 by 3t into e power minus 2t. Next is minus 1 by 2 into this one is e power minus t. In place of a, we'll have the 1. So e power minus 1 into t. Next, this one will be, so it is Laplace inverse of 1 by s minus a. It can be represented as e power t. Okay. So 1 by 6 into e power 1 into t. So in this way, you have to solve the Laplace transform. Okay, you have to solve the differential equation for a given by the help of the Laplace transform. So with the help of the initial conditions, we have evaluated the final general equation or the required solution for the given differential equation. Okay, by using the Laplace transform technique. So next we will go for the inverse Laplace. Sorry. Next we will go for the non-homogeneous differential equation. That is, and previously in homogeneous differential equation, the entire equation is equal to 0 here. Okay, it is equated to 0 here. And next, in this case, this differential equation is equal to 6 into cos 2t. So this type of form is called as a equation is called as a non-homogeneous differential form or differential equation. So apart from this, he has given the initial conditions in a different way. Okay. So previously it is of the form y of 0 is equal to 0. Y dash of 0 is equal to something like 2 or 3, whatever it may be. He will represent either in this way or he may represent in this way. So you have to check that if it is y is equal to 3, here it is given as y is equal to 3. It indicates that y of 0 is equal to 3. Why? Because he has given when t is equal to 0. So it is y of t is equal to some value. So it depends upon the t value. So when t is equal to 0, here he has given t is equal to 0. When y of 0, that is when t is equal to 0, y of 0 value is equal to 3. Okay, y of 0 value is equal to 3. And similarly, in the second case, d, capital D into y. So d is nothing but differentiation of y. That can be represented by y dash. So differentiation of y is equal to 1. That is y dash of 0 is equal to 1. So we have the y of 0 is equal to 3. Y dash of 0 is equal to 1. These are the initial conditions he has given from the given problem. So don't confuse. So simply, if he has given like that, then you have to put y of 0 is equal to 3. This can be d, capital D into y. So if he has given d square into y, then it indicates that y double dash. Y double dash of 0 is equal to whatever the initial condition value has given, that you have to put here. Okay. So in this way, you have to simplify the initial conditions when you have given this type of form. Okay, right. So now you have to write the given differential equation. Now you have to simplify this one, d square into y, d square y plus 1 into y is nothing but y is equal to 6 cos 2t. Now this can be simplified in a short notation, that is d square y can be written as y double dash plus y is equal to 6 cos 2t. Okay, right. So now what we have to do, so this is the simplification of the short notation form of the This is the short notation form of your the given differential equation. Now what we have to do? So we have to apply the Laplace transform on both sides. Okay, and by using the linearity property, you have to apply this Laplace transform on both sides. The Laplace transform y double dash plus Laplace transform y is equal to 6 into Laplace transform of cos 2. Okay, so Laplace transform y double dash is represented as s square y of s minus s into y of 0 minus y dash of 0. So this is for this equation. Okay, for this differential equation plus Laplace transform y is nothing but y of s. Okay, is equal to the right side part 6 into s by s square plus a square. A square value is nothing but 2. A value is nothing but 2 square. This is the equation. Now all these y of s terms will be kept at LHS side and remaining terms will be shifted to RHS side after substituting the initial conditions in the given equations. Okay, after substituting the initial conditions in this given equation. So s square into y of s minus what is y of 0 here? Y of 0 is nothing but 3. So 3s. Y of 0 value is 3. So that part is simplified in the next equation. So if you see here, so we have the initial condition s square into y of s square into y of s minus we have the initial term y of 0 is nothing but 3 into s minus y dash of 0 is 1 plus this y of s will be kept as same, that is equal to 6s by s square plus 4. So now this y of s terms which has to be taken common and which has to be placed at LHS side, which has to be taken at LHS side, y of s into so s square plus 1 square plus 1 that we got here. Okay, and now this minus 3s and minus 1 will be taken to RHS. Minus 3s, if it's shifted to RHS, then you will get it as a plus 3s, and next you will get it as a plus 1. This plus 1 minus 1 will be shifted to RHS, that you will get it as a plus 1, that is represented here. So finally, we need to find out this y of s. Y of s is equal to, so this s square term will be divided to this entire RHS equation. Okay, 6s by s square plus 4 plus 3s plus 1 by s square plus 1. So now we have to divide this s square plus 1 term individually to this numerator function. Okay, equally. Okay. So this one can be converted as, after dividing this term with respect to each and every term, 6s by s square plus 4 into s square plus 1 plus 3s by s square plus 1 plus 1 by s square plus 1. And this can be evaluated by using the formula. This can be evaluated by using the formula. When it comes to this can be solved or resolved by using the partial fraction method only. Okay, this can be simplified by partial fraction method only. Okay, so now this equation is represented of the form of, okay, non-repeated quadratic form. This equation is represented of the form of non-repeated quadratic form. It is not a repeated equation. See, we have a roots of s square, so it is of quadratic form s square plus as plus b. This is your quadratic equation. We don't have this as part or as term in the given equation. So this equation is compared. This equation is compared with respect to this quadratic form. Okay, then this type of function can be represented, okay, in such a way that by using the partial fraction, 6s by s square plus 4 into s square plus 1 is equal to, so it is a non-repeated quadratic factor. So when you have the quadratic factor of this type, then you can represent as as plus b. This partial fraction is divided as as plus b by s square plus 4 plus cs plus d by, sorry, cs plus d by s square plus 1. Okay, in this way you have to see. Okay, in this way you have to write the partial fraction for a given equation. Okay, for a given non-repeated quadratic factor equation or a function. Okay, right. So if you see carefully in this, now this has to be simplified in such a way that as into as plus b into, so this term, okay, this term is multiplied with respect to this, and this term is multiplied with respect to this, as plus b into s square plus 1 plus cs plus d into s square plus 4 by s square plus 4 into, after taking the LCM, s square plus 1. At the LHS side, you will have a 6s by s square plus 4 into s square plus 1. So this denominator term in the LHS and this denominator term in the LHS will get cancelled, and only numerator terms has to be equated both at LHS and at RHS. So from this, 6s is equal to, so multiply this one, okay, we get it as a as cube. Okay, if you simplify this one, you get it as a as into a square, you get it as a as cube plus as into 1, it is as. After that, b into s square, b is multiplied with respect to this whole term, it is bs square plus b plus, so this one cs into a square, that is cs cube plus cs into 4, that is 4cs plus d into a square, that is ds square plus b into 4, it is nothing but 40. Okay, so now what we have to do, so we have to take, first we have to check the, so first we have to see the s cube terms. Okay, we have to compare this s cube terms, that is nothing but, so if you see that we have the two s cube terms, so take s cube term as common here, so s cube into a plus c, okay, s cube into a plus c. So you have to take only s cube coefficient, that is a plus c into s cube. Next to s square coefficients, that is b plus d into s square. Next is plus, you have to take the s coefficient, that is a plus 4c, a plus 4c into s. Next to finally the constant term, that is b plus 4d. Yes, b plus 4d. Okay, b plus 4d. So now what we have to do? So from this equation, so we have to compare. Okay. So we have to compare the coefficients of LHS side and RHS side. That is equating the coefficients of like powers of s. Like powers of s is nothing but at the RHS side, that is at the RHS side you will have the s power 3 coefficient is a plus c, and you have to similarly compare the like power, that is s power 3 term at the LHS side. So if you don't have the s power 3 coefficient at the LHS side, then so you have to assume this as a 0. Okay, that is nothing but 0 is equal to, so we don't have the s power 3 coefficient term and the LHS side, that is nothing but 0 is equal to, in the RHS you have the a plus c. So we have to equate the coefficients of like powers of s. Okay, like powers of s at the LHS side and the RHS side. That is, you have to compare the coefficients of the powers, s power terms, both LHS and RHS. So by comparing this, you got a plus c is equal to 0. So from this, we got a is equal to minus c. And similarly, you can compare for s square, and you can compare for s, and you can compare for the constant. So if you compare all these things, so finally what you will get is nothing but, so we got the values for that. Okay, we got the values for that is nothing but, so b is equal to, so we got a is equal to 0 and c is equal to 0. So we got the values after simplifying, by equating the coefficients of like powers of s. We got a value as 0 and c value as 0, and we got b value as b is equal to minus, okay, 1 by 3, and d is equal to 1 by 3. Okay, we got the value as, okay, b is equal to minus 1 by 3 and d is equal to plus 1 by 3. Okay, right. So finally we got the value as, okay, so after simplification we got this value as 2s by, okay, 2s by s square plus 1 minus 2s by s square plus 4. So after simplification, that is, we got a plus as plus b by, we have s square plus 1. Okay, next plus cs plus d by something like s square plus 4. So we have the value as a is equal to 0 and b is equal, sorry, a is equal to 0 and b value as 1 by 3. Okay, and next c value as 0 and again d value as minus 1 by 3. So if you substitute a value as 0 here, sorry, we got the b value as 0 and d value as 0 and we got a value as minus 1 by 3, sorry, plus 1 by 3 and c value as 1 by 3. Okay, right. So in that way, after substituting the a value and c value in this equation, okay, finally we got that 2 into s by s square plus 1 minus s by s square plus 4 plus the second term will be same and the third term will be same. Okay, so this, in this way you have to simplify by using the partial fraction method. Okay, right. So after that, if you multiply this 2 into the internal term, you will get this 2s by s square plus 1 term. Here we will have the one more term plus 3s by s square plus 1 term. So 2s by s square plus 1 plus 3s by s square plus 1. If you add these two, you will get as a 5s by s square plus 1. Okay, next is minus 2s by s square plus 4. Next is plus 1 by s square plus 1. Okay, right. So after getting this y of s, after simplifying the partial fraction method or resolving by partial fraction method, we got this final y of s function. So now what we have to do? So now we have to apply the inverse Laplace transform on both sides in order to get the required solution. So for this, again you have to apply the linearity property. Laplace inverse of y of s is equal to phi into Laplace inverse of, that is, this phi is a constant which can be taken outside. Phi into Laplace inverse of s by s square plus 1. Next to minus 2 into Laplace inverse of s by s square plus 4 plus Laplace inverse of 1 by s square plus 1. So what is Laplace inverse of s by s square plus 1? It is nothing but, it is of the form Laplace inverse of s square by s square plus a square. That is nothing but cos a t. What is a value here? 1 square. Okay, 1 square. So cos t. So phi into cos t minus 2 into, it is again s by s square plus 4. That is s by s square plus a square. A value is nothing but, here 4 can be represented as 2 square. A value is 2. It is cos 2t. That is minus 2 cos 2t. And last one is nothing but, it is the formula which is same as 1 by s square plus a square. Laplace inverse of 1 by s square plus a square. That is nothing but 1 by a sine a. Okay, 1 by a sine a. That is nothing but, here a value is equal to 1. So 1 by 1 sine t. So we got this as sine t. Okay. So this is your required solution for a given differential equation with a constant coefficients. Okay. So this is the way you have to simplify the given problem when any differential, either homogeneous or non-homogeneous differential equations are given. So that can be done or simplified by using the simple Laplace transform technique. Okay, right. So these are the two questions which we have got in the previous papers. Okay, these are very important. So you have to solve, and I have explained this is the homogeneous differential equation form and this is the non-homogeneous differential form of equation. So I have explained the example for both the cases. Then you have to evaluate these two. And the assignment questions have been given here. You have to solve this one. If you don't get this one, you can ask me. Okay. Right. So reference textbook for this Laplace transform is nothing but, these are the 4 reference textbooks. So in this, B.V. Ramana and B.S. Agarwal is the standard. All these are standard textbooks, but the standard of this among these books are B.V. Ramana and B.S. Agarwal, which you can gain some knowledge on this Laplace transform. Okay, thank you.